Hello everyone, myself Pranav, and today I'll be discussing on topic AI in cognitive computing. Introduction to cognitive computing. Cognitive computing refers to systems that simulate human thought processes using AI machine learning and natural language processing. These systems are designed to learn, reason, and adapt by processing vast amount of structured and unstructured data. Unlike traditional computing, systems emphasize content aware decision making and probabilistic reasoning. Key components include perception, memory, attention, and language understanding model after human cognition. Cognitive computing enables applications such as medical diagnosis, financial forecasting, and intelligent assistance. Core AI technologies in cognitive systems. Machine learning algorithms, particularly neural networks, from the backbone of pattern recognition in cognitive systems. Natural language processing (NLP) enables systems to parse, understand, and generate human language using models like BERT and GPT. Computer vision integrates neural networks (CNNs) to interpret visual data with high accuracy. Knowledge representation uses ontologies and semantic networks to encode domain-specific information for reasoning. Reinforcement learning allows systems to improve decision making through trial and error interactions and with environments. Neural networks and deep learning. Artificial neural networks (ANNs) consist of layers of interconnected nodes that mimic biological neurons using weighted inputs and activation functions. Deep learning employs multiple hidden layers to extract hierarchical features from raw data, such as edges in images or phonemes in speech. Backpropagation computes gradients using the chain rule to update weights via optimization algorithms like stochastic gradient descent (SGD). Activation functions such as ReLU f of x equal to max of O comma x introduce nonlinearity, enabling complex function approximation. Loss functions like cross entropy h of p comma q equal to minus sigma p of x log q of x quantify prediction error during training. Natural language processing (NLP) fundamentals. Tokenization breaks text into words or subwords, enabling numerical representation via embeddings like word to vec or globe vec. Language models predict the probability of word sequences using n-grams or transformer-based architectures. Named entity recognition (NER) identifies entries such as persons, organizations, and locations using conditional random fields (CRFs) or BERT. Sentiment analysis classifies text polarity using supervised learning with labeled datasets and feature extraction. Attention mechanisms in transformers compute weighted sums of input representation to focus on relevant context dynamically. Knowledge representation and reasoning. Semantic networks represent knowledge as nodes, concepts, and edges relationships, enabling inference through graph transversal. Ontologies define formal specifications of domain concepts and their relationships using language like OWL, Web Ontology Language. First order logic (FOL) supports rule based reasoning with quantifiers and predicates. Example: bird of X gives rise to can fly of X. Bayesian networks model probabilistic dependencies among variables using directed acyclic graphs, DAGs, and conditional probability tables. Inference engines apply logical or probabilistic rules to derive new facts from existing knowledge bases. Cognitive architectures SOAR and ACTR. SOAR, State, Operator, and Result, is a cognitive architecture that models decision making through problems, spaces, and production rules. It uses a unified theory of cognition based on symbolic reasoning and reinforcement learning for skill acquisition. ACTR, Adaptive Control of Thought, Rational, integrates symbolic and subsymbolic processes to simulate human memory and learning. ACTR includes modules for declarative memory, procedural memory, and goal management interacting via a central production system. Both architectures support cognitive modeling in human computer interaction and intelligent tutoring systems. Machine learning in cognitive systems. Supervised learning trains models on labeled data using algorithms like support vector machines, SVMs, and kernel functions. Unsupervised learning identifies patterns in unlabeled data via clustering. Example k-means or dimensionality reduction. Example PCA. Semi-supervised learning combines limited labeled data with large unlabeled data sets to improve generalization. Transfer learning leverages pre-trained models. Example, RESNet BERT to adapt knowledge across domains using fine-tuning. Online learning updates models incrementally as new data arrives, crucial for real-time cognitive applications. Cognitive perception and sensor fusion. Cognitive systems integrate multimodal inputs, example, vision, audio, tactile, using sensor fusion techniques for robust perception. Kalman filters estimate system states by combining prediction with noisy sensor measurements using Gaussian distributors. Deep fusion networks process heterogeneous data streams to shade the latent representation in neural net architectures. Attention mechanisms weight sensors input dynamically based on contextual relevance and uncertainty. Perception, Perceptual reasoning combines sensory data with prior knowledge to infer high-level interpretations such as intent or emotion. Memory systems in cognitive AI. Working memory temporarily stores and manipulates information during cognitive tasks modeled using recurrent neural networks RNNs. Long-term memory encodes persistent knowledge using embeddings or knowledge graphs for retrieval and reasoning. Episodic memory records sequences of events implemented via memory augmented networks like differentiable neural networks. Semantic memory stores conceptual knowledge, often represented in ontologies or vector spaces with cosine similarity metrics. Memory consolidation in AI involves transferring learned patterns from short-term to long-term storage through rehearsal or replay. Reasoning and decision making. Deductive reasoning applies logical rules to derive conclusions from premises using a expert system and theorem provers. Inductive reasoning generalizes patterns from specific observations, forming the basis of machine learning models. Abductive reasoning infers the most likely explanation for observed data, crucial in diagnostic and forensic systems. Decision trees and Markov decision processes (MDPs) models sequential decision making under uncertainty with reward maximization. Application in real life. IBM Watson applies cognitive computing on to oncology by analyzing medical literature and patent records for treatment recommendations. Cognitive chatbots leverage NLP and dialogue management to provide context-aware customer support in real time. Smart manufacturing integrates cognitive systems for predictive maintenance using sensor data and anomaly detection. Cognitive tutors adapt educational contexts based on student performance and learning patterns using reinforcement learning. Challenges and limitations. Explainability remains a challenge as deep learning models often act as black boxes lacking interpretability. Data bias in training sets can lead to unfair or inaccurate cognitive decisions requiring rigorous fairness audits. Energy consumption of large models, example transformers, limits deployment in edge and mobile devices. Ethical concerns include private violations, autonomous decision making, and potential misuse in surveillance or warfare. Thank you.